Hello friends, welcome to our RV YouTube channel. Myself R Venkatesh. In today's session 30, under part 2 of electric drives and control, we are going to discuss about stator voltage control method of speed control of 3-phase induction motor using 3-phase AC voltage controller. So in this part 2, we are going to discuss how a 3-phase voltage controller works. In our previous session under part 1, we have discussed how the speed of a 3-phase induction motor can be controlled by means of using stator voltage control method. So for the stator voltage control method, we have made use of a 3-phase AC voltage controller in order to convert fixed AC input voltage to a variable AC output voltage, through which the stator voltage of a 3-phase induction motor is controlled, through which the speed and the torque are controlled. In today's session 30 under part 2, we are going to discuss how that particular 3-phase AC voltage controller actually operates. That means how a 3-phase AC voltage controller can convert a fixed 3-phase AC input voltage to a variable 3-phase AC output voltage. So let's start with the contents of this session. First, we are going to discuss about introduction, followed by the circuit diagram and the operation of 3-phase AC voltage controller with the help of waveforms. So first let us discuss about the introduction. So as we discussed earlier, a 3-phase AC voltage controller can convert a fixed 3-phase AC input voltage to a variable 3-phase AC output voltage. But here the frequency is not controlled. That means a 3-phase AC voltage controller cannot change the frequency. Frequency is constant, but the voltage can be controlled. Let us discuss about the circuit diagram of 3-phase AC voltage controller. So here fixed 3-phase AC supply, maybe a 450 volts. So a fixed 3-phase AC supply star connected, that is VAN, VBN and VCN is applied to the 3-phase AC voltage controller. Here the thyristor T1, T4, T3, T6, T5 and T2 forms the 3-phase AC voltage controller. So this fixed 3-phase AC supply is converted to the variable AC supply and which is fed to the impedance load. Here this is our impedance load, which is indicated as Z of 3 phases called phase A and the phase B and the phase C. Here since we are dealing with the speed control of 3-phase induction motor, we have considered our load as impedance load. And here it is also star connected. So input is also star connected and output is also star connected. Now let us discuss about the operation of 3-phase AC voltage controller. So for which we are going to consider the firing angle alpha as 60 degrees. That means we are going to operate this 3-phase AC voltage controller for the firing angle or the delay angle of 60 degrees. So here for that we have to draw the 3-phase input voltage. See here 3-phase AC supply of a 3-phase line to neutral voltage or phase to neutral voltage. That means phase voltage is given to the 3-phase AC voltage controller. So that phase voltage is drawn here. Okay, that is the voltage between a phase and the neutral, or the voltage between a line and the neutral is drawn here. So this VAN indicates the phase voltage between the phase A and the neutral N, and the VBN indicates the phase voltage between the line or the phase B and the neutral. Similarly here VCN indicates the phase voltage between the line C and the neutral. So this is our 3-phase line to neutral voltage. Okay, this is 3-phase voltage. Similarly here this is our 3-phase line to line voltage. Here this VAB and VBC and VCA indicates 3-phase line to line voltage. So in our next session 31, I will explain you in detail how to draw this 3-phase line to line voltage and this 3-phase phase to neutral voltage. So now let us discuss how the thyristors are triggered. Okay. So here if you look at this 3-phase voltage, here the first phase voltage is of VAN, that is positive half cycle of VAN. So to the positive half cycle of VAN, the thyristor T1 is connected. That means this thyristor T1 will get triggered at an angle of 60 degrees because we have chosen our firing angle as 60 degrees. So this VAN, positive half cycle of VAN starts at 0 degrees. So from here we have to leave 60 degrees. That means at an angle of 60 degrees, the thyristor T1 starts conducting. So if you look at this at an angle of 60 degrees, the positive half cycle of VAN is maximum when compared to the other phase voltages called VBN and VCN. Therefore, obviously the thyristor which is connected to the positive half cycle of VAN comes into the conduction. So therefore, here the thyristor T1 comes into the conduction at an angle of 60 degrees. So in this three-phase AC voltage controller, each thyristor is allowed to conduct for 120 degrees. From 60 degrees to 180 degrees, it becomes 120 degrees. Therefore, our thyristor T1 starts conducting at 60 degrees and completes its conduction at 180 degrees. So at an angle of 180 degrees, this thyristor T1 gets turned off. Okay, so next to the phase voltage VAN, our VBN phase voltage comes here. Okay, so this is positive half cycle of VBN. So to the positive half cycle of VBN, the thyristor T3 is connected. Therefore, here T3 comes into the conduction. Okay, so this VBN, positive half cycle of VBN, starts at 120 degrees. See here, starts at 120 degrees. From here, we have to leave 60 degrees because we have chosen our firing angle as 60 degrees. So 120 plus 60 becomes 180. Therefore, at an angle of 180 degrees, the thyristor T3, which is connected to the positive half cycle of the VBN, comes into the conduction. See here, at an angle of 180 degrees, the thyristor T3 comes into the conduction. So as we already said, each thyristor conducts for 120 degrees. So 180 plus 120 becomes 300. So our thyristor T3 starts conducting at 180 degrees and completes its conduction at an angle of 300 degrees. Okay. So next to the VBN, the voltage is of phase voltage is of VCN. See here. So this is positive half cycle of VCN. So to the positive half cycle of VCN, the thyristor T5 is connected. Therefore, thyristor T5 comes into the conduction. So this positive half cycle of VCN starts at 240. So from here we have to leave the firing angle of 60 degrees. That means at an angle of 300 degrees, the thyristor which is connected to the positive half cycle of VCN comes into the conduction. So as we already mentioned, the thyristor T5 is connected to the positive half cycle of the VCN. Therefore, at an angle of 300 degrees, the thyristor T5 comes into the conduction. So 300 and this thyristor T5 conducts for 120 degrees. So 300 plus 120 becomes 420. So this thyristor T5 conducts for an angle from 300 degrees to 420 degrees. So now let us discuss about the negative half cycle of thyristors also. So here the first negative half cycle of the phase voltage is VBN. See here this VBN. So the negative half cycle of the thyristor VBN which is connected is here is T6. See here the negative half cycle of the VBN is connected to the thyristor T6. Therefore, thyristor T6 conducts for this negative half cycle of VBN. So from here, this negative half cycle of VBN starts here. I mean minus 60 degrees. So from here we have to leave the firing angle of 60 degrees. So that means 0 degrees. Therefore, our thyristor T6 starts conducting at 0 degrees. So from here it has to conduct for a period of 120 degrees. That means it stops its conduction at 120 degrees. See here, the thyristor T6 which is connected to the negative half cycle of VBN starts conducting at 0 degrees up to 120 degrees. And the next negative half cycle of the phase voltage is VCN. See here, negative half cycle of phase voltage is VCN. So here negative half cycle of VCN is connected to the thyristor T2. So the negative half cycle of VCN starts at 60 degrees. See here, negative half cycle of VCN starts at 60 degrees. From here we have to leave the firing angle of 60 degrees. That means 60 plus 60 becomes 120 degrees. That means at an angle of 120 degrees, the thyristor which is connected to the negative half cycle of VCN comes into the conduction. So as we discussed earlier, the negative half cycle of VCN is connected to the thyristor T2. Therefore, at an angle of 120 degrees, the thyristor T2 comes into the conduction. So each thyristor is conducting for 120 degrees. That means 120 plus 120 becomes 240. Therefore, thyristor T2 conducts for a period from 120 degrees to 240 degrees. The next negative half cycle of the phase voltage is VAN. Okay. So to the negative half cycle of VAN, the thyristor T4 is connected here. See here, the negative half cycle of VAN is connected to T4, thyristor T4. Therefore, thyristor T4 comes into the conduction for the negative half cycle of VAN. This negative half cycle of VAN starts at an angle of 180 degrees. From here, we have to leave the firing angle of 60 degrees. That means 180 plus 60 becomes 240. Therefore, at an angle of 240 degrees, the thyristor T4 which is connected to the negative half cycle of VAN comes into the conduction. So from 240 plus 120 because each thyristor has to conduct for a period of 120 degrees. So 240 plus 120 becomes 360 degrees. Therefore, this thyristor T4 conducts from 240 degrees to 360 degrees. So this is how the thyristors are triggered. So based on triggering angles of the thyristors, now let us mark the pair of thyristors conduction periods. So from 60 degrees to 120 degrees, the thyristors T1 and T6 are conducting. And from 120 degrees to 180 degrees, the thyristors T1 and T2 are conducting. And from 180 degrees to 240 degrees, the thyristors T3 and T2 are conducting. And from 240 degrees to 300 degrees, the thyristors T3 and T4 are conducting. And from 300 degrees to 360 degrees, the thyristors T5 and T4 are conducting. And from 360 degrees to 420 degrees, the thyristors T5 and T6 are conducting. So now let us discuss the output voltage for this each periods. So the first period is the thyristors T1 and T6 are conducting. That means from 60 degrees to 120 degrees. So at this time what happens, let us see. So for this, please refer the circuit 1 here. The current starts flowing through the thyristor T1 and to the impedance load. That means our induction motor and to the thyristor T6. So here the voltage, the phase voltage which appears across our impedance load or the induction motor is VAN and VBN. Apply the voltage divider rule. So what the voltage divider rule says is V0. That means output voltage is equal to input voltage into R2 divided by R1 plus R2. Here our here this is for resistive load, but here we consider as impedance load, that is of Z in all phases, in A phase and B phase, in C phase, all phases the impedance load is of Z. So that means this becomes, here V0 is, we are intended to find our VAN, that is our output phase voltage across this impedance load. Okay, therefore our output is VAN. VAN is equal to input voltage Vin. So here input voltage is VAB. See here the input voltage is VAB. Therefore it becomes VAN is equal to VAB into Z by C plus Z becomes 2Z. If we simplify this, we will get the output phase voltage VAN is equal to 0.5 VAB. That means the output phase voltage which appears across this impedance load VAN is equal to 0.5 VAB. So now let us draw this VAN output phase voltage is 0.5 is equal to VAB here. So here this is our input voltage, line to line voltage, right? So this is our VAB. Okay, this is our VAB which has to be drawn for 60 degrees to 120 degrees. So from 60 degrees to 120 degrees, see from 60 degrees to 120 degrees, this is our VAB. So we have to draw off of this. That means here it is 0.5 VAB, right? Therefore half of it. So at least this much. Okay. So that is drawn here. 0.5 VAB. From 60 degrees to 120 degrees, the output phase voltage VAN across the impedance load is 0.5 VAB is drawn here. See 0.5 VAB. This 0.5 VAB is the trace of this one. Okay. And similarly, from 120 degrees to 180 degrees. Okay, from 120 degrees to 180 degrees, the thyristors T1 and T2 are conducting. So for this, let us refer the circuit 2. So from 120 degrees to 180 degrees, what happens is the current flows through the thyristor T1 and the impedance load and the thyristors T2. Okay, so the voltage which appears across our impedance load is VAN and VCN. So as we did like in the earlier mode, if we apply voltage divider rule, we will get the voltage across our output phase VAN is 0.5 VAC. That means the voltage across our impedance load is VAN is equal to 0.5 times the VAC. So this is for 120 degrees to 180 degrees. So 120 degrees to 180 degrees. See here, from 120 degrees to 180 degrees, this is our VAC. So the 0.5 times the VAC, the trace will be something like here. Okay, so this trace has to be followed. So 120 degrees to 180 degrees, this is our 0.5 VAC. Okay, so this is the half of the times of the trace of this VAC, because here it is 0.5 VAC, right? So this is how the output voltage for VAN during 120 degrees to 180 degrees is traced. And during 180 degrees to 240 degrees, T3 and T2 are conducting. So for this, let us see the circuit 3. So during 180 degrees to 240 degrees, the current flows through thyristor T3 and T2. Therefore, what happens is the voltage which appears across our impedance load are VBN and VCN. Therefore, here no VAN is flowing. The output voltage for phase A appears across the impedance load. Therefore, VAN is equal to 0. So 180 degrees to 240 degrees, here it is drawn as 0. See here. So during 240 degrees to 300 degrees, the thyristors T3 and T4 are conducting. So for this, please refer the circuit 4. So 240 degrees to 300 degrees. So during this period, the current flows from the thyristor T3 and to the impedance load and to the thyristor T4. So at this time, the voltage which appears across the impedance load are VAN and VBN. So if we apply the voltage divider rule, we will get the output voltage VAN, the output phase voltage VAN across the impedance load as minus 0.5 VAB, because this minus is due to the reversal of the input voltage. See here, so from 240 degrees to 300 degrees, here it is reversed. Here it is positive, whereas now it is negative. Therefore, see here, from 240 degrees to 300 degrees, here it is negative of VAB. Therefore, this negative is coming here. Therefore, during 240 degrees to 300 degrees, VAN is equal to minus 0.5 VAB. So that is drawn here. So this minus 0.5 VAB is the trace of this VAB. Okay. And at last, from 300 degrees to 360 degrees, the thyristors T5 and T4 are conducting. So for that, please refer the circuit 5. So from 300 to 360 degrees, the current flow is flowing from the thyristor T5 and to the thyristor T4. So at this time, the voltage which appears across our impedance load is VAN and VCN. So if we apply voltage divider rule for this, we will get VAN is equal to minus 0.5 VAC. So from 300 degrees to 360 degrees, this VAC is negative. See here, the VAC is reversed. Therefore, here it is minus. Therefore, from 300 to 360 degree, the output voltage VAN across our impedance load or the induction motor is VAN is equal to minus 0.5 VAC. So that is drawn here, minus 0.5 VAC in the negative axis. So this 0.5 VAC, that means minus 0.5 VAC is the trace of this one. Okay, from 300 to 360. So this is how we have drawn the output phase voltage VAN across our three-phase induction motor. So similarly, in this way, you can draw for VBN and VCN by yourself. If you have any doubt, you can feel free to comment in the comment box so that I will clear you how to draw this VBN and VCN.